All right, guys, we're going to get started on lesson 3.4. So let me present my screen. Okay. Okay, so in this lesson, we're going to be talking about perpendicular bisectors and a few theorems that have to do with perpendiculars. All right, so we'll get started with the vocabulary. We've already talked about a bisector. We talked about a segment bisector and an angle bisector. So we know the term bisect means cut in half, okay? Perpendicular, we know what that term means. We learned that earlier in this chapter as well. So when two lines are perpendicular, they intersect to form a right angle. So put those two ideas together and you have a perpendicular bisector. All right, so perpendicular bisector, any segment, line, or plane that intersects a segment at its midpoint forming a right angle. So if you have this segment AB, and then you have this line PQ, and P is the midpoint, and we know it's the midpoint because of the two little tick marks. AP is marks congruent to PB, okay? So this is, PQ, is the bisector of segment AB because it's cutting through the midpoint, right? Over here, similar, but a little bit different, we again have a segment JK and R is in the middle. We know R is in the middle because JR is marked congruent to KR. So that means that RS, that line, is going through the midpoint of segment JK. Therefore, RS is bisecting JK. But because it's going through and forming a right angle, because it's perpendicular, we give it a more specific name. We call it the perpendicular bisector, all right? And here, distance from a point to a line. The length of a perpendicular segment from a point to a line, okay? The distance between point A and line K is AB. So if you have a line, I'll just draw another quick little diagram. If you have a line, imagine that's straight, and then you have a point not on the line. If you want to know how far away that point is to the line, you're going to measure it by sketching a perpendicular segment down to that line, and that perpendicular segment, that segment there, is going to represent the distance from the point to the line, okay? All right, let me move on. Next, we have a total of 3 theorems. I'm going to write down the shorthand that we're going to be using in our proofs if we need to use these theorems in our proof. So the first theorem, and look at the diagram as we read, it says, if two lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. All right, so it says if angle 1 is congruent to angle 2, then this line G is perpendicular to this line H. And that's because if we have a straight line, we know the two angles have to add up to 180 degrees, right? And if those two angles are equal, then that means they're both 90 degrees, right? 180 divided by 2. And if they're 90 degrees, that means it's a right angle. And if that's a right angle, that means that the lines are perpendicular. So in a theorem, or excuse me, in a proof, if we wanted to use this theorem, we would say congruent adjacent angles implies perpendicular lines. Okay. Congruent adjacent angles implies perpendicular lines. All right, moving on. The next theorem is the perpendicular transversal theorem, which says in a plane, if a transversal is perpendicular to one of two parallel lines, then it is perpendicular to the other. So in this diagram, if H and K are parallel to each other, if J is perpendicular to H, then J also has to be perpendicular to K, which makes sense because even if we talk about like corresponding angles for a second, if we have parallel lines cut by a transversal, I know corresponding angles, this angle here and this angle here, corresponding angles are congruent. So this angle right here would also have to be a right angle. All right, so if J is perpendicular to one line, J is going to be perpendicular to both lines, assuming those two lines are parallel. Okay, so in a theorem, we would just call this the perpendicular transversal theorem. And to be honest with you, I don't know if I've ever actually used this theorem in a proof. Not saying that you can't, I just don't think I have. All right, so we don't use it very often. It's more going to be used for looking at diagrams and doing algebraic problems. All right, let me scroll down. Next is the lines perpendicular to a transversal theorem. It says in a plane, if two lines are perpendicular to the same line, then they are parallel to each other. Again, kind of makes sense with what we already studied. If this angle is 90 degrees and this angle is 90 degrees, because they are corresponding angles, that means the lines are parallel. So if I was trying to prove the lines are parallel, that's what I would end up using. I would say corresponding angles congruent implies parallel lines. However, you could use this theorem as well, and we would just write lines perpendicular to transversal theorem. So there's really no shorthand for it so much, just a few abbreviations. Again, I don't think I've ever used, I know for sure actually, I've never used this theorem in a proof. If I was proving that those lines are parallel, I would say corresponding angles congruent implies parallel lines. That's how I would go about proving the lines are parallel. But again, just knowing that the lines are parallel by looking at the diagram is going to help you with the algebraic problems that we're going to be taking a look at. Okay. All right, let me keep on moving along. All right, we are going to look at one problem here. Let's look at problem number 2. All right, it says, find the distance from point A to BC. And there's 3 different segments to look at. We have AC, AD, and AB. So think about what we talked about earlier with the vocabulary, the second term we talked about, which was distance to a line from a point, right? How do we find the distance from a line, from line BC to point A? Do we want to use segment AC to calculate distance, segment AD, or segment AB? We want to use segment AD. You want to use that perpendicular segment. So you're going to find the distance. Oh, I need my pen. Find AD. Okay, when I say find AD, that means find the distance. So we're going to use the distance formula. AD is going to equal the square root difference of the x's. So the x coordinate of A is -3, the x coordinate of D is 3. So -3 minus 3 squared plus the difference of the y's. -4 minus 2 squared. -4 minus 2 squared. All right, so PEMDAS, order of operation, simplify inside parentheses first. So -3 minus 3, that's -3 plus -3, that is a -6 squared, plus -2 minus 2, that's -2 plus -4 plus -2, that's going to give you -6 squared as well. So then continuing with PEMDAS, you're going to evaluate your exponents. So I have 36 plus 36, which is going to give you the square root of 72, right? If I was simplifying my square roots, I would break that into the square root of 36 times the square root of 2. And the reason I break it down, the reason I break it down that way is because 36 is a perfect square. That's 6 root 2. Okay, so if I was asking for the answer left in terms of a radical or the exact answer, this would be the answer I was looking for. If the direction said round, which they don't say here, but we're going to round as well. If the direction said round to the nearest 10th or 100th, I'd plug it into my calculator. And when I do that, let me see if I can get my calculator real fast so I can show you how to plug it in. Let me see if it opens for me. clear this. All right, so I'm just putting in there 6 and then square root of 2 to get a decimal approximation. You get approximately 8.49. All right, so it's approximately, gotta get my pen now, 8.49 units. Okay. All right, so just make sure you're using the perpendicular segment when measuring the distance, okay? Let's move on. In exercises 5 through 8, determine which lines, if any, must be parallel. Explain your reasoning. Okay, so we're trying to use the theorems from earlier in class to determine whether or not any lines are parallel. So I see that P is perpendicular to S, or you can say it the opposite way, S is perpendicular to P. But does that allow me to conclude any lines are parallel? It does not. There's not enough information for that problem. Not enough info to use any of the theorems we talked about. All right. For the next problem, number 6. So this time I see that R is perpendicular to both P and Q. So since R is perpendicular to both P and Q, that means P and Q have to be parallel. All right. P is parallel to Q. Now, as far as your reasoning, I would say corresponding angles congruent implies parallel lines. However, I'm recording myself right now so they can see you. Can you give me a few minutes?
Mom.
Go ahead.
Can I please have dessert?
Yes.
Thank you.
All right. So anyway, sorry about that. He's getting himself dessert right now. What was I even saying? Oh, so if I was proving that they were parallel, I would say corresponding angles congruent implies parallel lines, and that would be a fine justification. Using the theorems we discussed today, we would say that lines perpendicular to transversal theorem is the reason that they are parallel to each other. Okay. Let's go on to the next one. Okay. So for this next one, I see that M, right, is perpendicular to both J and K. All right. I also see that K is perpendicular to both L and N. So we actually have 2 sets of parallel lines. You know that M and, I can't draw an arrow. Let me try that again. You know that M and N are parallel because K is perpendicular to both of them. So you could say M is parallel to N because K is perpendicular to both. That's not like the real theorem, but I'm just explaining it. And then likewise, you know that J is parallel to K because N is perpendicular to both. So J is parallel to K because M is perpendicular to both. All right. And for both of those, I just kind of explained it, but that's again using the lines perpendicular to transversal theorem. Okay. All right. And number 8. So for number 8, we have that angle 1 and angle 2 are congruent and adjacent. Right? Remember that first theorem we talked about? So we could say that, what did I say? Congruent adjacent angles implies perpendicular lines. right? So because congruent adjacent angles implies perpendicular lines, that means that N is perpendicular to S. N is perpendicular to S. So I have a right angle here. I know they're both 90-degree angles. Then, since I see that N is perpendicular to both S and T, I know that S and T have to be parallel to each other. So I can say that S is parallel to T because N is perpendicular to both. That again is using that lines perpendicular to transversal theorem. All right, and then we actually have one more thing to say. Now, let me just kind of erase some of this stuff. Put that right angle box back here. Because S, see how S is perpendicular to N and S is also perpendicular to M. So that would mean that M and N have to be parallel to each other. So M and N are parallel because S is perpendicular to both, and that once again is using that same theorem, the lines perpendicular to transversal theorem. Okay. All right, guys, that was a pretty quick lesson for today. Get rid of that and pull you guys back up. Sorry about the interruption. I will see you guys back here for the next lesson. Bye.